Hello and welcome back to another episode of Zeiss Micro Minute. I'm Michael Kemplin and I'm one of the applications engineers at the Zeiss Microscopy Center Innovation Center in California. I'm going to be going through a topic today that is semiconductor specific. It's passive voltage contrast imaging on the FESIM, but it can be used on other materials if you know the properties of the materials, but it's usually regarded with respect to the semiconductor and fault isolation failure analysis. There is just to do some housekeeping here, I'm going to remain on the screen the whole time and show you some of it as some tutorial stuff I'll go through first, and then I'll show some of the live imaging on the tool itself. And then I'll go ahead and do a little brief overview of what some of the results were and some tips and tricks along the way. Just a reminder that you can put any questions you have in the chat that's on the right and the YouTube channel. All right, so let's go ahead and move forward with this. And let me start with an introduction to what is passive voltage contrast, especially with respect to a FESIM. I'm going to go live here. You should see an image now. And so let's go back to the beginning here. So passive voltage contrast can be due, especially on semiconductors and things, due to the capacitance, grounding issues, junctions, PN junctions specifically. Active voltage contrast is when you actually have a nanoprobe or probes coming down and landing on the sample itself, and you're biasing the sample or parts of the sample. You can do it with E-beam probing as well. So we're not going to talk about that today, but we'll talk about the passive voltage contrast and how that's used, how you can leverage the FESIM to leverage that. So the definition of passive voltage contrast is a difference in detection yield of the secondary electrons across different regions of the sample in response to the scanning of the beam. So the beam's scanning across the sample and it picks up different signal from different areas. And especially if you have repetitive structures on the sample, you should see the same type or generally the same type of contrast and brightness from the same type of structure. And if you do, then everything's good. Generally, if it's faulty, something that's faulty or something that's different than anything else around it, it'll look different in the passive voltage contrast image. So uses is inspection for metal opens and shorts, inspections of PN junctions, anomalies. They hunt for different defects. Sometimes they're large, sometimes they're small. Sometimes it's a leaky gate or things of that sort. And it's kind of use the SEM to find those as you're looking at the die. Normally you're polishing the die to a different level, or if pulled it out on a wafer lot, you'd pull it out at a particular level and image and check for failures. So on capacitance, this is the sort of behavior that you get where you get electron causes charge buildup, fewer escape, or you get a reservoir where there's a bunch of them that are repelled and escape from there. This is some of what you'd see on a short versus a long line having different contrast. They have different capacitances, so you'll see that, and that's a good example of how the contrast and brightness of those lines, even though they're physically the same, they're going to have different capacitance, and they respond to the electron beam differently. If you have contrast due to the grounding, this occurs here. You got a floating side or grounded side. Floating side's going to capture the electrons and so look darker, and then the grounded side's going to send off the secondary electrons, and the detector emits it up to the detector, and they're very bright. So if you look at a SRAM array, you see something like this where you can see that the P plus and N plus of the active, which we call RX, the contacts are bright, but then the pass gates are very dark, even though they're all the same material they're made out of physically, that they're just connected differently. And therefore, and then this is a good example of an open on a PFET. There's InFET. So tips with respect to this Gemini SEM and other SEMs, that if you wanted to Just leave this up right now. I'm not going to go through this because this isn't this is just to give us some background, and then I'll go into the actual live portion and that's basically wanted to show you how it's used and how you might use it on your sample. And then you definitely want to plasma clean because otherwise the carbon will build up. You're going to be using lower voltages. Today I'll show you some 300 volt and 500 volt images at different currents. So you're using very low voltage, and typically you're using an in-lens through lens detector, and then you're wanting to optimize the beam parameters and see what voltage and what current combination really brings out the contrast differences between some of the features that you're wanting to. So that's what I'm going to show during the video today. So let me go ahead and exit out of that. And if I go to the tool itself, I recorded some stuff here from the tool. I'm on a Gemini Sim 460, which is able to have infinite control over the kV and current. So what you do, and I'll pause it in a moment when I show the user interface. Okay, so if I see at the down at the data bar at the bottom, I can double click on any of those things, the magnification, the AHT, or the current, and I can choose any current and any kV combination because it is a single aperture double condenser lens design whereas the traditional Sims have apertures, and it works both ways. It doesn't really matter. That it's just a nice feature to have. It makes it extremely easy to use. At the very top, there's, of course, there are Zeiss macros that they're buttons basically that I've set up. You can customize them. I've just set up the fast, medium, slow scans, and then a couple of different types of photo acquisitions, including a drift-corrected frame integration, and what that means is that it's integrating a certain number of frames, and it's doing a drift correction algorithm between them and overlaying them and building up to get a better signal to noise. It's very useful when you're doing fast scanning speeds, which actually is the way to go when you're doing passive voltage contrast, because the longer you dwell, it changes the properties and how many electrons are being absorbed, and you get really, your contrast kind of degrades as you go to a slower scan speed. I'll go and continue here. So we're on an SRAM part of a chip. We're down at the contact level. This is just a polished chip that I have it's an older chip from a while back, and it actually turns out to be really nice as far as a die. So just kind of zoom in here. And like I said, you can double click here and change the magnification and change it to 25,000 magnification here. You can see that these are SRAM block. There's all the repeating structures. And if I pause it for a moment, you can see there's small bands of dark alternating with dark and bright. And so we're already picking up some of the passive voltage contrast. Just to make a note that I'm at 300 volts and 250 picoamps, so very low voltage. Typically would recommend starting at a very low voltage so you don't impact the properties of any of your transistors, especially if you want to find where the defect's at and then later do nanoprobing on it for nanoprobing analysis. All right, so let's continue on here and go back to the lower mag. This just happens to be an SRAM block that's relatively clean. Like I said, I polished it, and there's always going to be, you can see where I've imaged at one point, so we'll try to avoid that one. That's just a little bit of carbon buildup, and plasma cleaner will take care of that. But for now, we'll zoom in on the neighboring area here. All right, so taking a slow scan, this is a scan speed 9. You can see where there is some bright areas, and that you still see the dark in between them, but the dark isn't nearly as dark when we're doing a really slow scan like this. So what I'll do is go and save that, and we'll move on to doing a drift-corrected frame integration image with a faster scan speed of 5 and averaging about 20 frames. And you can see where it does bring out the contrast a lot better. So faster scan speed with more frame integration actually works a lot better for the passive voltage contrast imaging. But throughout the video, I'm going to be doing both so we can see and compare. So zoom into 50,000 mag here, just move around. I'm going to move to the edge of the SRAM block here. Change the brightness contrast just to make it a little more, not quite as bright. And we're doing a slow scan again. You see where it had been pretty dark and now they're in between is not quite as dark. So it's a little more difficult to pick up where those subtle differences are between the contacts. Whereas if we do a drift corrected frame integration, and again, I just press on the button up here because it brings in these parameters, and I just quickly choose the scan speed and number of frames, and then starts the acquisition, which is indicated down here on the bottom. And we see that the contrast is improved again. So the faster scan speeds work out quite a bit nicer. And even faster than this is probably doable, up to scan speed of 2 or 3. So 2, 3, 4 is probably ideal. For these, I'm using the scan speed 5. It seems to work fine. All right, so the next, let's say that I want to know what is the effect of the current on the passive voltage contrast. So I'm at 250, so I'm going to drop it down to 100 picoamps. We'll see what it looks like at 100 picoamps. What's going to happen, go ahead and do some alignment here, zoom in and do some focus, stigmation, and wobble. But what's going to happen is that our signal is going to be lower, and then it's not going to be exciting as much. So it's not going to, I'm going to show that it's not going to get as nice of a signal. So we're not going to get as nice of a contrast when we drop to this low of a current. Let's move up to the top of the block again. Let's see, maybe over in the middle here. You can definitely see on the left edge here where the sense amps are that we're picking up a lot of different good voltage contrast. There's some dark areas right next to the bright areas. Now some of this, most of this is passive voltage contrast, but you have to be aware that if you do at more of the advanced materials that down at the contact, metal 0, and local interconnect level, that you can have things other than tungsten. You can have molybdenum and other elements than cobalt and things that may end up resulting in different contrasts. So this one looks pretty nice. We're still picking up the contrasty part of it. It's just not quite as pronounced as what we had done before when we were at the higher current. So if we take a drift corrected frame integration, let's use 15 frames here, just make it faster. And there's a little bit of contrast, but not much. It's not nearly like what you want. So it seems like we've gone a little bit too low on our current. So let's go ahead and zoom out here. Let's make it live. I want to change it to 500 picoamps, so it's going to be double what we had originally when I first started showing you this. Again, you need to go through the focus, stigmation, and wobble because we're at such a low accelerating voltage that it does impact that. It doesn't take more than about 30, 40 seconds or so here to do. You just have to make sure that everything is looking nice. Just doing a little fine tuning on the stigmation. There we go. That's looking a lot nicer. Let's pop it back out here. So let's find an area that looks nice. So probably back up near the top again of that block. And again, you can double click in anything that's down in the data zone and it'll change the parameters. So I'm going to change the magnification. It's higher magnification back to about 25,000 mag here. Again, we're seeing the contrast really nicely on the edges of the blocks, the sense amps and things. Within the block itself, now we're picking up quite a bit of the brightness, the contrasty difference between the brights and the darks. So it definitely makes a difference going up higher in current. I could go up higher even than this, but we're not going to for the sake of time today. It just gives a little bit of a flavor for what you have to do kind of initially when you go and you're wondering what parameters might be best for the imaging that you're actually doing. And it'll vary depending upon whether you're down at the base, like the the contact level or the active level, or whether you're at metal or local interconnects or up at metal 1, metal 2, things like that. So in most cases, most of these are done down at the front end level. All right, so doing once again, drift corrected frame integration. Seeing it's picking up nice contrast on these all. If we go ahead and zoom in to double the mag here to 50,000 mag, a little bit of stigmation and focus correction. We'll take in a couple images of that as well. So notice that even at 300 volts, it's really easy. I could easily drop it to 200 volts, and it does go down to as low as 50 volts, but most of the time you're going to stay somewhere in the neighborhood of 200, 300 volts initially to do this. Gives enough signal. So now we're seeing these are very accentuated, bright, next to some of these that are medium, and then there's some that are a little bit less. So there's about 3 different levels of grayscale that I can see that are on these different contexts. And we don't have any defects that I know of in this, so everything's going to look the same. If it weren't, it'd stick out like a sore thumb, basically. It would call out, and you could see where it would be different than its neighbors. Even though it should look the same, then that would lead you to believe that you should do some nanoprobing or do some other imaging potentially, whether it's cross-section or TMML or something like that. All right, so now we see that if you do, just changing the scan speed here, started with really good contrast. I'm going slower in scan speed and kind of losing the contrast. You can see where the slower you go, it has enough signal where it just starts washing out on the contrast. So definitely on this, like scan speed of 5 or 4, even 3, worked really well, and with the drift corrected frame integration. All right, so let's go back down. So we tried currents. Now, what is the effect of the voltage on the passive voltage contrast? So let's bump it up to 500 volts. We're at 300, now we're going to be at 500. I left it at 500 picoamps since that seemed to be a good amount of current. So it's a good place to start, at least with the next iteration up here. Just doing some fine-tuning the focus didn't wobble. Notice that the area of interest doesn't move. I mean, it stays the same. You change the voltage, it stays right there. You don't have to go find in your area or anything. So it's really super easy to use on the tool here. All right, so now we got a nice looking image. We go back to 25,000 mag. And now we see where it's quite a bit more accentuated between the areas that bright and the dark. Very contrasty. So this is actually working really nice at 500 volts and 500 picoamps. So this is what we're looking for. We're really looking for bringing out that contrast and having enough signal so that you can do this. All right, so I'm going to take another series at double the mag once I acquire the drift corrected frame integration one here. This one should have a little better contrast than what we had before even, which it does. So we're starting to see a nice, so these seem to be ideal conditions. What you do is you continue doing this and go to like 700 volts. Seems like 500 picoamps is ideal. You could try a nanoamp, but it may eventually get washed out again. There's a point beyond which you have too much current and it washes out again. And I'll show that on the results when we get at the very end of this. So it's looking nice. I'm back at 50,000 magnification. You can see where all the contacts are pretty dark, and then the cascades and other features in this are like a medium gray, and then you got the middle parts of the cell and things like the pull-ups, pull-downs, and things that are different contrast. Do the drift corrected frame integration image here. So just to recap, we've changed from 300 volt to 500 volt, and we've tried different currents, and we found that at this point the 500 volt and the 500 picoamps work the best. It is possible that the slightly higher voltage and or current might work better. So just for the sake of time though, I'm not going to go through that. What I'll do now is I'm going to switch back to my other monitor, and let's bring up the results. So on the die that we were just on, you can see where there's 300 volts, 500 volts, 700 volts at 25,000 mag. This was at 250 picoamps. And you can see where the contrast gets better and better as we went up. And this was a 700 volt image. I didn't show that today, but I went ahead and acquired it when I was on the tool. So it turns out that 700 volts is even better as far as the contrast. So go up even higher. So this one's kind of a toss between 500 and 700. So either one works fine. As we saw today, the 500 was working really nicely as well. If we check the currents now, the lower currents don't tend to have as good of contrast as the higher currents. And that's kind of to be expected. Now, there was another die that we've done before and we've shown. These are 5 nanometer SRAM cells. The SE2 shows the topography, so you can see where we have oxide on top of the actual gates and metal thing, and only the contacts have been exposed at this point. There's a logic area at the top and the SRAM, that, like what we were just doing on the bottom left and bottom right. These were done on a tool that actually had discrete apertures, which can be done, and it's fine. They had about 250 picoamps of current on this, far as I recall. And so we're getting nice contrast between all of these different PN and pull-ups, pull-downs, pass gates, and things of that sort within these structures. If I go to the next one, these are the Inland series that was done. In this case, we dropped it down to starting with 100 volts, went to 200, went to 400 volts, 600, 800, 1 kV, 1.1, and 1.2 kV. So you start getting at the higher voltages, you see where it starts getting washed out again. 1 kV is not quite as good as 800 volt. 800 volts is really nice and contrasty compared to 600. And as you drop, then there's a point at which it inverts. And that's due to, there's a charge balance point. And there's an equation that actually shows where that would be. So that's the low point of everything. So you still can get contrast. It's just not what you're actually looking for. So you want to stay above the region when you're seeing this and flip it back into the normal where contacts are bright and the background is black or a dark gray. All right, so just to show you final one on that die, the 15, 30, 60, and 20 micron aperture series, and I put the smallest is the 60 picoamps, and then they go into about 240 picoamps, 950 picoamps, and then 1.8 nanoamps. So you can see where too much current on the bottom right one washes things out. And then at the top left, if you have too low of a current, you just don't have quite enough current to show a nice contrast. So somewhere in between, it seems like a lot of times I've found that anywhere between 250, 500, and 1 nanoamp, kind of good points to try and see on your die. It all depends upon, like I said, where you're at and where you're polished, which layer you're on. All right, so let me get out of that. And that's all I have. If you have any questions, then you can put them in the chat box and we can answer them, or we can get back to you. You can always send an email to us and get back to you with the answers. If you'd like to know more about passive voltage contrast, or if you'd like to know more about different things, each week we'll be here on this channel. Go ahead and put this up. The upcoming workshops, the QR codes on the upper left, our overall work The portal that we have for Zeiss that has different things for customers is in the middle, and then upcoming live streams, including the Micro Minutes, which is every Thursday at 1 p.m. You click on that QR code and you'll see there is another one that's coming up next week, and it's on X-ray microscopy, which is high aspect ratio imaging. So we'll look forward to doing that next week and continuing our series throughout the whole year. And we look forward to you joining us again next week, and hopefully every week thereafter at the same time. I'll stay on here for a moment longer just to make sure that there are no questions, but otherwise I'm going to let everybody go and have a nice day.